Soil Dynamics, Understanding Earthquake Forces. Welcome back to Blueprint to Reality, the channel where we uncover the science and engineering behind the world's strongest structures. When we think of earthquakes, most of us imagine buildings swaying, bridges cracking, or towers trembling. But what truly drives this destruction begins not in the structure, but in the soil beneath it. The science that studies how soil responds to earthquakes is called soil dynamics, and it's the hidden key to understanding why some structures survive while others collapse. Today, we'll dive into soil dynamics, exploring how earthquake forces interact with the ground and what engineers do to keep our foundations safe. Why soil dynamics matter in earthquake zones. Soil isn't just dirt. It's a complex mix of particles, water, and air that behaves in unexpected ways when shaken. In a quake, soil can amplify vibrations, weaken under stress, or even transform from solid ground into a flowing liquid. That means the same earthquake can have very different effects depending on whether a building sits on bedrock, sand, clay, or reclaimed land. During an earthquake, soils face three main challenges. 1. Ground motion amplification. Soft soils can magnify shaking, making earthquakes feel much stronger than they are. 2. Resonance with structures. Soil and buildings each have natural frequencies. If they align, vibrations intensify, often leading to collapse. 3. Soil instability. Under strong shaking, soils may lose strength or even fail completely, causing landslides, settlements, or liquefaction. Real example: in the 1985 Mexico City earthquake, seismic waves traveled hundreds of kilometers, but the city's soft clay amplified shaking up to 8 times stronger than nearby areas on firmer ground. Hundreds of buildings collapsed, proving that soil dynamics can be more dangerous than the earthquake itself. Key concepts in soil dynamics. 1. Seismic waves and soil response. Earthquakes generate P waves, fast, compressional, S waves, slower, shear, and surface waves. Soft soils absorb and re-radiate these waves, often increasing their intensity. Example: bedrock sites may shake briefly, while soft valley soils can trap waves, making shaking last longer. 2. Resonance and natural frequency. Every soil layer has a frequency based on its stiffness and depth. If this frequency matches that of a building, resonance occurs, amplifying motion. Example: mid-rise buildings in Mexico City resonated with the soft clay layer, while shorter and taller buildings fared better. 3. Liquefaction. Occurs when water-saturated sandy soils lose strength and act like liquid under shaking. This causes tilting, sinking, or total collapse of structures. Example: during the 1964 Niigata earthquake in Japan, entire apartment blocks tipped over without breaking, as the ground beneath them liquefied. 4. Landslides and slope failures. Earthquakes trigger mass movements of soil and rock, especially on steep slopes. Example: in the 2008 Sichuan earthquake, thousands of earthquake-induced landslides buried roads and villages, causing as much damage as the shaking itself. Engineering applications of soil dynamics. 1. Site characterization. Engineers perform geotechnical surveys to understand soil type, stiffness, and water content. This helps predict how the soil will behave during quakes. 2. Ground improvement techniques. Compaction, grouting, stone columns, and vibro replacement strengthen soils against liquefaction. Drains and dewatering systems reduce pore water pressure in sandy soils. 3. Seismic design codes. Modern building codes require engineers to consider soil amplification factors, ensuring structures can handle site-specific shaking intensities. 4. Foundation strategies. On soft soils, deep foundations such as piles transfer loads to more stable layers. Base isolation systems help separate buildings from soil-induced vibrations. Lessons from real-world earthquakes. Mexico City, 1985, amplification on soft clay caused devastation. Lesson: never underestimate soil resonance. Niigata, Japan, 1964, liquefaction caused buildings to sink intact. Lesson: water-saturated sands are dangerous. Christchurch, New Zealand, 2011, liquefaction destroyed roads and buried pipes. Lesson: underground infrastructure must also be designed for soil failure. Sichuan, China, 2008, earthquake-induced landslides caused massive loss of life. Lesson: slope stability is as critical as foundation design. The future of soil dynamics research. Soil dynamics is advancing with new tools and technologies. Seismic microzonation, mapping cities by soil type to predict shaking intensity block by block. Smart sensors, embedding sensors in soil to measure stress and pore pressure during real earthquakes. Numerical modeling, advanced computer simulations to predict soil structure interaction with high accuracy. Resilient design, integrating soil improvement, flexible foundations, and seismic isolation for layered protection. Conclusion. Soil dynamics reveals a hidden truth: it's not just the strength of a building that determines survival, but the behavior of the ground beneath it. From amplification to liquefaction, the soil can either protect or betray us in an earthquake. By understanding and engineering for these forces, we can design cities that remain standing even when the ground itself moves. Thanks for watching Blueprint to Reality. If this video gave you a new perspective on earthquake engineering, give it a like and share it. And let me know in the comments, should I make a deep dive episode just on liquefaction and its real-world disasters? Don't forget to subscribe for more engineering explained, one blueprint at a time.